Okay, so too late. Um, so last time, here's what we talked about. Um, given a stress tensor, uh, um, the eigenvalues of the stress tensor eigenvalues of sigma are the three principal stresses um, that's the maximum possible normal stress, the minimum possible normal stress. And when I say possible, what am I talking about? This is all sort of confusing. I mean, it takes a while to sort of wrap your head around it all, I think. So what, when I say maximum possible, minimum possible, what am I talking about? What? So I'm talking about at that single point, you can rotate the coordinate system all these different ways, and some values would, some coordinate systems would give you big values, some would give you small values, but you'd never find a coordinate system that gave you a more positive value than one of them, and you'd never find a coordinate system that gave you a more negative value than the other one. So that's what I mean by possible. You can look forever at that point with all these different coordinate systems, and you'll never beat those. Um, and then there's one in between. Um, the eigenvectors, um, it takes a little fiddling to get it, but they give you directions of the coordinate axes in the principal coordinate system. So these are the axes of the principal coordinate system. Um, and now here's the new thing. It turns out that it's not really the maximum and minimum uh, normal stresses that we're looking for most of the time. Um, what we really want, uh, what the eigenvalues or the principal stresses are most useful for, so what the principal stresses are the most useful for, yeah, you ran too fast at the Mall of America. Oh, well, that did not work very well. Um, is finding the maximum absolute value of the shear stress. Um, and so, yeah, you take the eigenvalues, they give you these maximum and minimum normal stresses, but that's not really what we're looking for the most part, most of the time, especially with the more brittle the materials, the more important this is. What we're looking for is the maximum absolute value of shear force. So again, like at that point, you can rotate the coordinate system all these different ways. And when you find a coordinate system with the maximum absolute value of shear stress, uh, that maximum absolute value of shear stress is a good predictor of damage or failure. Okay, so how do you do that? So to find the maximum, people just call it the maximum shear stress, but remember we're talking about absolute value. With shear stress, there's not really any fundamental difference between positive and negative. So one thing you can do is really a rotation, transform the principal stress tensor to a coordinate system that's rotated 45 degrees about the axis of the middle eigenvalue. Okay, that sounds sort of wordy, but the idea is simple. So when you have your principal stress tensor, you have three values on the diagonal of the stress tensor, this way to you. The x diagonal position is the x normal stress. The y diagonal position is the y normal stress, and then the z normal stress is the third one. And whichever one of those three is the middle value of stress, okay, rotate about that corresponding axis, you know. So if your middle one is in the x position, rotate 45 degrees about the x-axis. And you get this new stress tensor that has a maximum shear stress when you take its absolute value. That's the hard way to do it. It's not that hard, but there's an easier way to do it. The benefit of that is it'll give you the whole stress tensor. If all you want is that maximum shear stress, then let sigma 1 and sigma 3 be the max and min principal stresses, respectively. Yeah. Then, so this one's the most positive. This one's the least positive or most negative. Then the maximum shear stress is the maximum principal stress minus the minimum principal stress divided by 2. So if all you want is that maximum shear stress value, then you can just use that simple formula and calculate it. And if you don't want to worry about any of the other elements in that matrix. Okay, let's do an example. Okay, so let's say the stress tensor is 190, 910, 000 megapascals. So first give principal stress tensor. Then calculate the maximum shear stress, just using that formula. And then last, we'll do that coordinate system transformation. So we'll calculate a stress tensor that has the maximum absolute value of shear stress. And B and C have to agree. Okay, so when we take the biggest absolute value out of this stress tensor, it has to match our answer for B that we get from that formula. Okay, or else I'm a liar. Or we made a mistake. Okay, so the easiest way to calculate the principal stresses is just to plug it into a calculator. But I have this set up to just turn into a quadratic. So let's go through the calculation. So A, just make your calculator do it. 4. So now we're going to take, so we have 1 minus lambda, 9, 0, then 9, 1 minus lambda, 0, then 0, 0, minus lambda. And we want to set that determinant equal to 0. So we have 1 minus lambda times the quantity, 1 minus lambda times negative lambda, minus 0. Then we have 9 times the quantity, negative 9 lambda minus 0. And then we have plus 0 is equal to 0. And if we multiply this out, we get, so we have 1 minus lambda times 1 minus lambda times negative lambda plus 81 lambda is equal to 0. So let's pull a lambda out of everything, and let's switch the signs. So we have lambda times this stuff that's 1 minus lambda times 1 minus lambda minus 81 is equal to 0. And you can already see, since we've factored out this lambda, one of the roots is lambda equal to 0. Okay, yes. I did, yes. Well, and then I multiplied both sides by negative 1. Okay, so lambda equals 0 is a root. So now we just need the other two. And 1 minus 2 lambda plus lambda squared minus 81 is equal to 0. So we have lambda squared minus 2 lambda minus 80 is equal to 0. And now you can just, use whatever quadratic formula solver you have. This factors into nice numbers, but just use the quadratic formula. But this factors into lambda minus 10, lambda plus 8, I believe. Lambda is equal to positive 10, negative 8. Okay, so the principal stresses. I'm going to do them in order from biggest to littlest. So we have positive 10, 0, and negative 8. In this case, and these are all megapascals, in this case, we did have our maximum was positive and our minimum was negative, but that doesn't have to be the case. You can have, 10, 4, and 2, or you can have negative 2, negative 6, negative 20, or whatever. And so what's the principal stress tensor? Well, there's a bunch of them. You could do 10, 0, negative 8. By a bunch, I guess there's exactly 3. You can move those around anywhere along the diagonal. 0, wait, no, permutations. So there's a whole bunch, 6. Yeah, 0, 10, negative 8. Let's not do them all. Or, okay, any of those are fine. The thing is, you just need to have those 3 principal stress tensors on the diagonal and zeros everywhere else. And what those correspond to is, so if this is, so we're saying our 10 is on the x-axis, our 0 is on the y-axis, or our 10 is on the x face, y face, z face. Okay, this one is just saying the y-axis here is the x-axis that we had here. So it's just 90-degree rotations of these things give different permutations of those. Okay, that's the meaning of those. I'm going to use this one. It's not any better or anything, but I'm just going to use that one. All right, so next we want to calculate the maximum shear stress. And so that's equal to the maximum principal stress minus the minimum principal stress divided by 2. And so that's equal to 9 megapascals. Okay, so you can find, so if you rotate the coordinate system of this maximum shear stress in 90-degree versions, you can get nines and negative nines and stuff, but you can't get anything with a bigger absolute value than that as a shear stress. You can get it as a normal stress maybe, but not as a shear stress. So now let's do a, by the way, look at the original stress tensor for this problem, and we had 9 in these shear stress elements, which means that this is a version of the stress tensor with the maximum shear stress, the one that we started with. Okay, so now say we want the stress tensor at that maximum shear stress. Excuse me. Corresponds to that maximum shear stress. How are we going to get that? Well, in this one we're choosing here, so our principal stress tensor is 10, 0, negative 8, zeros everywhere else. What axis corresponds to our middle eigenvalue? Y, yep. Middle, that's not middle. Eigenvalue corresponds to Y. So we're going to rotate 45 degrees about the Y axis. We're going to rotate the coordinate system 45 degrees about Y. You could also rotate negative 45 degrees. It would work out just as well. So the rotation matrix is cosine of 45, 0, negative sine of 45, positive 45. 0, 1, 0, sine of 45, 0, cosine of 45. .7071, 0, negative 0.7071, 0, 1, 0, 0.7071, 0, 0.7071. And so now the stress tensor with a max shear stress equal to 0.7071, 0, negative 0.7071, 0, 1, 0, 0.7071, 0, 0.7071, multiplied by that shear stress with diagonals of 10, 0, negative 8. Multiplied by Q transpose, 0.7071, 0, 0.7071, 0, 1, 0, negative 0.7071, 0, 0.7071. Anybody doing this? Okay. 1, 0, 9, 0, 0, 0, 9, 0, 1. Yeah. I mean, the fact that we came out with a 9 in a shear stress position makes me think. So we came out with this stress tensor that wasn't, so like I said, we happened to start with one that had a maximum shear. We didn't get that one back. We got some 90-degree rotated version of that one. But we got the same answer for what's the maximum absolute value of shear stress and a tensor that corresponds to it. Anybody have any questions about any of those calculations? Anybody want to, so how did I get this? What did I do to get this? Started with some matrix, and it turned out that its eigenvalues were even, were positive 10 and negative 8 and 0. Nice, simple numbers. How would you go about making something like that happen? Like me, when I was making the problem. I think answering this question sort of helps square away how all these things relate to each other, I think. Yes, well, not, that's the right way of thinking. I mean, I picked a principal stress tensor, and then I just rotated it some amount. So I picked a principal stress tensor of 10, 0, negative 8, and then just spun it a little, spun the coordinate system a little. I happened to do it 45 degrees was how much I rotated the coordinate system, which is why the thing that I got to start the problem with had a maximum shear stress in it. If I had started with a principal stress tensor and done a coordinate system transformation at 20 degrees or something, I wouldn't have gotten those maximum shear stresses. Yep. Yeah, you can put those in any position, but then you just wouldn't rotate about y. You'd rotate about the axis wherever the 0 is of your principal stress. You know what I mean? So if we had used this second one instead, we would have had to do our 45-degree rotation about the x-axis. Yep, the middle one. No, it would probably be a 90-degree rotation of it, but it would still give you the same values. They'd just be moved around. Any other questions about that? Yeah. Oh, I'm not sure. I'd have to think about that. I think that, yes, here's why I think it is. I think so what we have is, it's not exactly a principal coordinate system that you get, although you can think of it that way. It's really a principal quadrilateral where faces have to be oriented a certain way. And then you can call those faces whatever you want as long as they satisfy the right-handed coordinate system requirements. And so I think the 6 permutations of each thing correspond to axes facing in the 6 different directions that are all 90 degrees apart. But there'd be more than that one there. I don't know. I have to think about that. I got to be honest, I'm probably not going to. Okay, so now we are almost done with everything we need to know about the relationships between stresses and strains and manipulating stress tensors. Okay. There's one more thing I want to talk about, and that is the tensile test. But I want to talk about the tensile test if you do it all the way to failure. So we've talked about using a tensile test to calculate Young's modulus and Poisson's ratio. But Poisson's ratio and Young's modulus come from the linear elastic range of the material. Okay, so you don't get to stretch this material very far before, or you definitely don't have to, and it doesn't do any good to stretch it very far. You just pull on it a little bit and calculate those values. But usually when you do a tensile test of a material, you continue pulling on it until you start to get permanent deformation, and then you get necking, it's called, where the middle starts to thin out, and then it really starts stretching, and finally it breaks apart. It's really loud, by the way. So let's think about what happens on a stress versus strain graph. So this is the stress, and this is the strain. And this is what happens for most engineering materials, and it happens for metals. Okay, so when you first start pulling on it, well, before you start pulling on it, what's the stress? 0. What's the strain? 0. So we know that it starts here. Okay. And then you start pulling on it and you get something like that. Depending on what your units are, it's steeper or less steep. Until you get to some point, A. And this is the region that this class deals with. This is the linear elastic region. And then after it reaches this point, you start to get nonlinear behavior around the same time you start to get permanent deformation. They don't always exactly line up, but it's close. And you start to get something like this. And that can extend farther, or it can be shorter. But this is nonlinear. Well, you can see it's nonlinear. It stops being a line. And it's plastic deformation, permanent deformation. And then it starts to have this negative slope, which means even if you reduce the force a little bit, it would still be stretching. It's basically getting a lot weaker until you get to some point B, at which point it starts to get stiffer again, and then eventually somewhere up here it breaks, and now it's in 2 pieces. So this region is what this class is about. There's a lot of stuff that goes on with this material after anything that this class deals with. After A is the plastic deformation, then you get to this point B, and after the point B, that thing where it starts to get stiffer again, that's sort of weird. You wouldn't really think necessarily that that would happen, but this is called strain hardening. And also, by the way, right around here, you start to get a difference in these values depending on how you calculate the stress. This is called true strain, true stress, true strain. The black line is called the engineering stress and strain. And the difference between these two, this is where necking starts to happen. So necking is so the blue and black lines separate when necking begins. Um, and I'm just going to draw a picture of necking. So this sample starts to thin out in the middle as you apply these forces. And so to calculate the true stress and the true strain, you're actually using the current measurement of the cross-sectional area to do your calculation of stress and strain. Okay. And so the engineering strain, you're just using the original cross-sectional area. And so if you're dividing by a smaller cross-sectional area, the stress values are going to get bigger. And that's why the true strain, when it starts to neck, starts to get much bigger than the engineering stress. Okay. So anyways, that's just some sort of terminology that sometimes comes up. But if you have to, if you're like running out of brain space and there's only one thing that you can, you only have space to remember one thing about all of this tensile test stuff, it's that this small region on the left is the only thing that this class is capable of dealing with. Yep. It doesn't, yeah, when they start to separate, the true will always be bigger at every point because you're dividing that stress. Remember, to calculate the stress, you're taking the force divided by the cross-sectional area. And so if you're dividing by a smaller cross-sectional area, it just increases the value. But the shape stays the same. Yep. Oh, no, I think, not that I know of. I think you just do it because they're sort of more sophisticated than what we're doing in this class. There are ways to predict when something's going to fail. And so you can use this to figure out how to calculate when something is going to fail. There are a lot of cases where, like, you don't mind plastic deformation. And so for us, all we can do is, like, when we talk about, and that point A, actually, that reminds me is an important, so A is called the yield stress. And that says when permanent deformation is going to start. But And so using the methods in this class, we can calculate when permanent deformation is going to start. But in most engineering applications, you don't really care when permanent deformation starts. You're fine with permanent deformation starting. You just want to make sure it doesn't break, you know. And so if you can figure out a way to calculate when that's going to happen, or when, at least when this crazy stuff is going to start to happen here, then that's a little more useful. Yep. Yes, it does. I don't remember exactly how, but yeah, it does. Any other questions? Yep. It depends on the application, I think. In some cases, you don't want any permanent deformation, and so you want to stop before that. In other cases, you don't care whether it bends, you know, as long as it stays strong, you know. So, by the way, what mathematical thing about this graph tells us Young's modulus? Yep. Yeah, good. Yeah, so this, the slope in this region is Young's modulus. Okay, there's one more little thing I wanted to say. So this is sort of back to the max shear stress. Brittle materials usually fail in shear. And one application of this that really shows how all these things fit together is compression fractures, bone compression fractures. It's also true of like stakes of wood or any kind of brittle material that fails by compressing it. Um, so in an X-ray, if you're looking at like a femur that's been in a car accident and fails due to compression, that's a pretty common, like you hit your feet on the front of the, under the steering wheel and get a compression fracture. What it looks like is this. And the reason it looks like that is that the forces are being applied in this direction. And so the principal stress tensor has one axis this way, one this way, and one this way. Okay, that's the principal coordinate system. And therefore, the coordinate system where shear stress is maximum is oriented at 45 degrees from that. And so the breaks happen at that angle because bones are weaker when subjected to shear stress than they are when subjected to compression or tensile stress. And so they're most susceptible to breaking along that, in that direction where the maximum shear stress occurs. Pretty interesting. Okay, that's all. Have a good weekend. So we don't have school on Monday. So see you Wednesday.